This demo picks up from the previous linear statics and normal modes analysis and extends into an investigation of the dynamic behavior of the bracket model with a frequency response analysis. The bracket model is a sheet metal structure that is fixed at the base and has an electric motor attached. The motor is modeled using a mass element representing the mass of the motor attached to a node positioned at the motor center of gravity. The motor center of gravity node is linked to the bracket at the attachment hole with a spider of rigid elements. The presence of the motor completely changes the dynamic characteristics of the bracket structure. The statics analysis showed that the bracket structure was not heavily loaded and the deflection of the motor center of gravity node was 0.345 mm and less than the maximum allowable of 1 mm. However, there may be some base vibration that could affect the dynamic behavior of the bracket. This frequency response will show the dynamic response of the bracket subjected to a dynamic excitation across a defined frequency range. First, we will create another spider of rigid elements to connect all the attachment holes in the base to one single node. We do this using the Custom Tools icon to access an API program that creates a spider connection from curves to a central point. And so now all of the base attachment holes are linked by the spider of rigid elements to one single node at the center. This makes it easier to set up the loads and boundary conditions. Next, we will define a new constraint set to constrain the one central node point. Change the set ID to 2 and the title to fixed base. Within the new constraint set definition in the model info tree, right-click Constraint Definitions and select Nodal. Now we pick the central node and select the fixed for the constraint definitions. You can verify constraint creation visually by switching on the View Constraints toggle. Next, we'll set up the dynamic loading definition. We'll be running a direct frequency response analysis and we'll set an overall structural damping coefficient of 0.1. Now we need to set up a function to define the sweep of base excitation frequencies that will dynamically load the model. In the first definition, we set a general range from 0 Hz to 50 Hz in 5 Hz steps. However, we know from the normal modes analysis that the first natural frequency of the structure is 26.5 Hz, so we'll define a more detailed frequency sweep between 20 Hz and 30 Hz in 1 Hz steps in order to pick up this region of more extreme dynamic behavior with greater accuracy. In addition to the already defined gravity loading, these excitation frequencies load the model through the base, so we need to define a unit load at the base node of the model acting in the z direction. Another function definition is required to specify the magnitude of the loading as it acts across the range of frequencies. In this case, we'll maintain a unit loading across the frequency range. With the loading and constraint definitions completed, we'll turn the View Constraints and View Loads toggles off to clean up the display of the model. Now the model is ready for analysis. From the Model Info tree, we set up a new analysis for a frequency response by right-clicking Analyses, selecting Manage, and then selecting New. We can enter a title for the analysis set and set the analysis type to frequency response. It's also a good idea to check that we're picking up the right boundary conditions. We can do that by expanding the relevant entries on the Analysis Set Manager dialog. Once we're happy that everything is OK, we can set the analysis off to run. NX-Nastran now starts to run and perform the analysis. We can keep a check on progress as the analysis is running with the Analysis Monitor window. When the analysis completes, the results are automatically read into the Femap database. With the analysis now complete, the results can be viewed. First, we'll close the Analysis Monitor window and select the View Select icon in the View toolbar. This is where we can view the results at the point of interest, the motor center of gravity point, across the frequency range in an XY plot. All the data required to set up this XY plot is entered in the View Select dialog. The XY plot shows the Z translation of the motor center of gravity point. You can see that close to the first natural frequency at 26 Hz, there's a displacement of 3.312 mm, showing a dynamic magnification factor of almost 10 over the static response. The static response is visible at the left at 0 Hz. A more refined frequency sweep would probably reveal an even higher displacement value. Therefore, with the requirement to maintain a deflection of less than 1 mm at the motor center of gravity node, any dynamic base excitation loading with a frequency between 20 Hz and 30 Hz would require a redesign of the bracket. This shows that in many cases, a simple static analysis review is not enough. Femap with NX-Nastran can take the analysis further and model a more realistic representation of the design and its working environment to give more accurate and complete answers.